Hello there, ladies and gentlemen. Welcome to my YouTube channel. My name is Fredrik Byström Sjödin, and today we're going to talk about RCBs, residual current breakers, type A and DC currents, a growing problem. RCBs, in Sweden we call them jordfelsbrytare, is a common security device used worldwide. Type A is a type of RCBs that has problems with dealing with DC currents that exceeds 6 milliamps of DC. And that can cause some interesting challenges in our networks, electrical networks, and our installations. So I will show you. Here we have a common electrical grid, 3 houses, dwellings, like in any suburbia in Europe or Scandinavia. We have a TN system, 400 volts AC, 3-phase. The house to the left has a PV system with solar panels on the roof with an inverter. The house in the middle has bought an electric vehicle that is plugged in and charged. And the house to the right has nothing of that, just a simple electrical installation covered by an RCB type A. And the other houses has also RCB type A, as you can see. Right? Nothing special with this. We have millions of dwellings or electrical installations looking like this all over Europe. All right. In common operation, the flow of currents on the AC side is like this. The current flows through the load and back through the neutral conductor, and we have no residual current in our RCBs, and everything works just fine, right? And in this particular example, we have a slight malfunction in the inverter on the left house, causing it to emit 10 milliamps of DC out into the grid, going somewhere. And that's that. Nothing spectacular about that either. Everything works, functions as it should. And through the neutral conductor is also flowing a current of 10 milliamps of DC in this example from the inverter in the electric vehicle. And this is an example. The DC can of course flow through the line conductor as well, or through both. But to make an example, I put it this way with the orange arrows, right? 10 milliamps. And that, of course, could cause a problem for the RCBs that are installed in the house in the middle, because the DC exceeds 6 milliamps. We get a residual current through the DC to the RCB, and that will make the RCB to get a malfunction. They will remain in the on position and not trip if you have a residual current on the AC side over 30 milliamps. So, and that's not very comfortable because as an owner of installation, you don't know whether your RCB is working or not. So that's not good, right? And then we have in the house to the right, we have a human or kid in this example living, and we have a malfunction on the load causing an earth fault through the human body like this. Nothing, of course, it's spectacular. It's a human body, but it's a fault that can occur, of course. In this example, it's above, it exceeds 30 milliamps AC, which should cause the RCB to the right to trip, right? But then again, we have this DC current from the solar panel on the left and the DC current from the EV, the electric vehicle, in the middle. And perhaps it will flow through as a fault current through the RCB to the right, causing a residual current through the RCB and through the earth fault down to ground. And since this DC exceeds 6 milliamps, in this example it's 20 milliamps, we will get a malfunction on the RCB and the house to the right. And that, of course, is not very satisfying at all, because the owner of the house to the right perhaps has no idea that any neighbor has bought an electric vehicle or a solar panel systems somewhere. He's totally unaware of that and finds out the hard way when he has a fault in his electrical installation. Right? Not good. And then to make another example, we have the house to the left. We have a common earth fault on the load to the ground that's not exceeding 30 milliamps AC in this example. And we get perhaps a DC current, residual current through the RCB through and down to the ground as well, causing the RCB in the house to the left to get a malfunction. And this is something that is unacceptable if it's a problem. Is it a problem or not? Well, actually, we don't know really. From the research I've done, it's hard to, no one can tell how the DC currents flows in this kind of installations that are connected like this in a grid. To me, that's a risk. And if it's a risk, we have to deal with it somehow. So for time being, I consider this as a risk and something we have to be aware of. So people out there, watch out for the DC currents when you have RCBs type A. Right. That's all, folks, for now. My name is Fredrik Bysen-Sjödin. This is my Instagram and my YouTube channel. And please subscribe if you think this is interesting. I work as a technical expert on the Swedish Installation Federation. Bye-bye. See you next time.